burning. And that same part is the part that is good to breathe. The rest of us doesn't. The rest of the air doesn't do us any good. Breathe in and it doesn't burn. So those actually those two types of air came to be called by some chemists the fire air, which is the portion of the air that burns, and then foul air was the portion of the air that doesn't. Yes.
So heat fire,
Yeah.
if you took a casserole or something, put it in the water and you just put it underwater, would it burn for a second? Or
If you did what? Put it underwater?
if you just took it, if you took the Greek fire and put it underwater,
Oh
without
yeah.
letting it touch and then you let it touch,
Oh no, it needs
You put it in the balloon and then pop it.
oh, it needs oxygen it needs the fire air in addition to the water in order to burn. Okay, so you couldn't actually, that's right, you couldn't just add water to it in isolation and have it burn. Okay. Yes,
So
true.
if you threw a whole bunch of it on a boat and you just it touched water, you threw it a whole bunch on the boat and then you just took a hose and squirted on it, it would just.
Well, you wouldn't, if the boat's in the water, then as soon as you throw this stuff on the side of the boat, it touches it's against the boat and it's touching the water, and the flames will just break out at the water line and start burning the boat.
That's why.
So, yeah.
will the fire burn on top of the water?
Yeah, it will. You'll
Like if you have a
see
match,
flames right on the surface of the water if you throw this stuff on the water.
But what is it burning? What is it?
Hmm?
What is it burning? It's like if you have a match and it's lit,
Yeah.
as soon as there's no more wood, then the fire goes out.
Well, it's gasoline will burn. If you light a match to gasoline, right? So that's what's. Part of this Greek fire was gasoline, and another part was this phosphorus compound that ignites when combined with water. So that's what's actually happening. Okay, let's. Okay, so Mayau made this important discovery that air is not a pure stuff, the way the Greeks had assumed, that it has these two components, and one burns and one doesn't. Now, the next useful discovery was made by a guy, Stephen Hale, and he didn't make any great discoveries in chemistry, as far as the nature of chemical compounds or anything, but he invented an apparatus which turned out to be extremely useful. So he's worth mentioning just for that reason. So he invented an apparatus for collecting gases.
What was that called?
I call it an apparatus for collecting gases. In 1727. And what this was is he could, it was really simple. All he did was he took a, let's say you have, a big bucket of water. And you take a bottle that's full of water and you invert it in here. Okay, so you've got some bottle. And the bottle is initially full of water, okay?
How did you get it full of water? Did
Well, you
pour
just
water?
start it out full of water and then invert it. Now the water won't run out. Why?
Because of the air pressure on the oil.
Right, exactly. The air pressure out here keeps the water raised up in the
Oh,
bottom.
like-
Hmm?
Like when you're in the pool and you take like a plastic cup and turn it upside down.
Yeah, right. It doesn't just fall out the water, right? It stays. In fact, Galileo was the one who discovered exactly how high the column of water has to be, you know, before you actually see it fall down. And it was. Does anybody remember the number? I think. Yeah, it's like 33 feet. Yeah, but yeah, it's a lot. So, okay, so you just have this simple apparatus. Yes.
Does it matter like if it just has to be 20 to 33 feet? What if it's like maybe 5 feet tall but it's really, really wide? Would that matter or not?
No, doesn't matter. 33 feet high. That's what the water. That's what the air pressure will. That's how much water it will push up. Push up water 33 feet. Now. So all Hale did here was, let's say you have a piece of tube now that you run. You run into this glass container with the water in it, and you know over here, you attach this thing to. Well, let's say you have another glass container here with some chemicals in it, and you know you do something to these chemicals. Let's say you heat them up or whatever, and you generate a gas from whatever chemical reaction you have going here. Well, the gas is just going to go through the tube and bubble up into this container, right? And then the water level will come down, and you'll end up with a container full of whatever gas you generated over here. Yeah, true.
So it won't push the container up like up and the container stay in the same place. It'll just let the water go down.
Yeah, the water just will drop down as soon as it's. I mean, if obviously, what would you expect to happen if you poked a hole in this container up here?
With water or gas?
Yeah, I mean, let's say you just you poke a hole in the top of the container so it's open to the air out here. What would happen to the water level?
Probably leak down.
Yeah, it would just fall right down to the water level of this big bath that it's in, right? So, I mean, that's in effect what will happen. I mean, you're not letting the air in this case, but you're letting a gas in. So the same thing's going to happen. The water level is just going to fall down. Yeah.
So in there, how long will the gas last? Like, would it just vary or would it?
Well, I mean, it would last in there forever until you let it escape. So basically, Hale invented a way to collect gases from chemical reactions. Now, I mean, it's a pretty simple idea, but no one had thought of it before him. And now it turns out he didn't do much with this idea. I mean, he did a bunch of chemical reactions, and he saw the gas was bubbling up in his container, but then he couldn't really think of experiments to do on these gases to determine their properties, so he didn't really discover any gases. But the guys that followed Hale did figure out ways of experimenting with the gases they collected. So his apparatus was put to good use, it just wasn't put to very good use by him. Okay. So let's see how it was put to good use. Okay, so that was 1727. Just to test your other scientific knowledge, what else was going on around 1727? Any ideas? Think about what was going on in electricity. Yeah, Dan. No, that was later. Troy?
Not Volta.
No, that was, remember, the battery was invented at around 1800, right? So 1727 actually happens to be the year that Newton died. It was only a few years after that Gray found that he could transfer electricity from one object to another through these wet strings that I told you about. So he discovered electrical conduction. And then Dufay did his experiments where he discovered two different kinds of electricity, attraction and repulsion. So we covered all that. Well, that's what's going on in electricity around this same time that chemistry is just getting started. Okay, now the next guy I want to tell you about that did something important with Hale's apparatus is Joseph Black. And he discovered a new gas, which he called fixed air. And he did that in 1754. So that's only a couple of years after Franklin's kite experiment. Nick?
Are these guys all Russian?
Oh, no, these, actually the guys that I've told you about are all English. In Black's case, Scottish, if you want to be exact. He lived in Edinburgh. Okay. Well, by the time Black is doing his research, scientists had discovered another kind of metal, magnesium. And he was experimenting with this magnesium. And he had it in some form which it was combined with some other stuff, so it wasn't pure magnesium. It was what he called magnesium alba, but it was what we call today magnesium carbonate. So he had something, let's just call it magnesium carbonate. And he found that when he heated this up to high temperatures, so magnesium carbonate plus heat, it would go to a different magnesium ore plus some gas. Okay, so in other words, he's got this apparatus of Hales that I just drew on the board, and he's got this magnesium carbonate in it, and basically he puts a flame underneath it and he heats it up. And he sees a gas bubbling out of it and into his container. Now, the question is, what is this gas? Well, he starts doing experiments on it, and he finds that it doesn't burn. You can't breathe it, or at least animals can't breathe it. Now, you might think, well, it's just like the foul air, the inert part of air. Well, it discovers a difference, though. Plants love this stuff. Plants will thrive in it. Okay. And after a plant has been in it for a while, then the air starts to support combustion and respiration again. So obviously this is it's a different kind of gas than just the inert part of air, the unburnable part of air was. So this is something new. And in fact, what he had discovered was carbon dioxide, which we now abbreviate as CO2. And after some more investigating, Black actually discovered different ways of producing this same gas. I mean, he could take a piece of chalk and again heat it up, and it would turn into a certain compound that had been found in limestone that they called quicklime back then, plus this same gas that he called fixed air. Okay, so there was the second reaction he discovered. I'll just I can put this in different ways, but chalk plus heat goes to quicklime plus the CO2, or what Black called the fixed air. In modern notation, I'll just give you.
All right, so explain how a slice really good learning how to manipulate people's perceptions and the importance of tuning and knowledge. Okay, so seeing but not being seen, or observing but not being observed. This is the art of being a spot.
What's going on here? We now know that this chalk that Black was working with is it's a compound of calcium and carbon and oxygen, and if you heat it up, it'll go to a calcium oxygen compound plus the carbon dioxide gas that Black discovered. So that was, and now scientists know of 3 different gases. There's this one, and then there's 2 components of air. Yeah, Nick.
So now do people, do people know that to separate gases from material?
Yeah, I mean they're using obviously they're using heat to decompose these chemicals, and also to I mean, to compose the chemicals too, in some cases. I mean, sometimes when you add heat, you'll get something to burn, and that turns out to be actually bringing together the substance with the air, right? So it's actually so it can work either way. Heat can break up chemical compounds, or heat can actually be used to bring them together in some other cases. Okay.
Okay.
Oh, by the way, the Black didn't discover this, but a guy that followed Black, another chemist that I'm just about to tell you about, Joseph Priestley, he figured out that this fixed air stuff that Black had discovered was soluble in water, and that he figured out how to carbonate water, make soda water.
All right. So that's a very brief update.
So that was done, I think, in the 1760s. So the first, they figured out how to. This was the scientific foundation for soda.
What's up since that?
Okay. So let's go to, let me see, the next guy, the father of soda, Joseph Priestley.
Maybe some rich actually.
No, he gave it away. I mean, he told his friends that ran breweries about this process and how you can carbonate water, and they went off and did it and made money out of it. He just gave the idea away. So he should have got a patent before he went and told everybody about it.
It's not fair.
No. Okay, but actually he was a smart guy. Maybe not when it came to money matters, but when it came to,
He's financially stupid.
maybe he was financially slow, but he was scientifically fast. And he made a very, very important discovery in 1774. He discovered oxygen. What he did was he had a compound. Well, it was a mercury that had rusted, basically. If you leave mercury out under certain conditions, it will turn red. Okay? And so he had this rusted red mercury, and he also had this huge magnifying glass. So he took his huge magnifying glass and he heated up a piece of this red rusted mercury to very high temperatures, and he found that he could make the red rusted mercury go back to pure mercury, and a gas would bubble off. And he collected that gas in the way that using the Hale apparatus, and then he did experiments on it and found that it was just like the portion of the air that supported combustion and respiration. Only it did it much better than ordinary air. Well, let's just get this down. So he starts out with this let's just call it rusted mercury, plus heat, intense heat from this huge magnifying glass that he's got. And it goes to pure mercury plus a gas. Now, he tries burning this gas, and he finds that it burns really vigorously. I mean, better than ordinary air. He breathes it, and it's great to breathe.
Did you personally breathe it or did you put an animal?
No, he personally breathed it. So yeah, shows a little. So he might have been not smart on money matters, but he had some courage, huh? So yeah, and if you put a mouse in a container of this gas, the mouse lived a lot longer than it did if you put it in a container of ordinary air.
So it still died?
Well, eventually it'll still die.
So he'd keep the mice
No, but
there
it
for like
stayed.
years.
Well, no, I mean his containers weren't that big, so the mice wouldn't last years. But he would, right, keep them there till they eventually suffocated, and time to see how long it took them. But no, the mice were all volunteers, so it was okay.
I wonder who volunteered.
So Priestley figures out what he has done is he has generated in pure form this fire air. I mean, the part of ordinary air that burns and is breathable. And later, another chemist, whom we'll get to probably next week, would name this gas oxygen. But at this point, right, it was just the burnable part of the air. Now he discovered other ways of doing this same thing. I mean, you don't have to do it with mercury. He found there were other metals that if you took other rusted metals and heated them up enough, you could generate the oxygen. So now we're up to. I mean, this was very important because now chemists knew that this was this part of the air that was burnable and breathable was not something unique to air. You could actually generate it in pure form from other materials. Okay. Well, let's keep going here. Now, let me, that was the most important discovery that Priestley made in chemistry. So let's leave him and go to the next really smart guy on this list. It's a name that should be familiar to you. Cavendish. What did Cavendish do that I've already told you about? Something smart.
And this was this year?
It was last year, wasn't it?
Last year.
Was I there then?
who found the G gravitational thing?
Yeah, right. He was the guy who determined the strength of the gravitational force, basically, by taking, right, exactly. He took two big lead balls that were hanging on a, by a torsion, on a torsion balance, and he saw these balls rotate. I mean, put smaller little balls next to him that on a rotating apparatus, so he could measure the strength of this force. Basically, the same way that Coulomb measured the strength of the electrical force, with that torsion balance, if you remember. So, yeah, Cavendish was the one who figured out the big G in that gravitational equation, which allowed him actually to figure out the mass of the Earth, for instance. So it's definitely,
Last year?
yeah, it's last year. Okay, so this, what he does in chemistry, he did a lot of chemical experiments too, in addition to his physics, and he discovers yet another kind of gas. Let me see. Actually, I'm not sure. I don't have the year down for this one, but it was also in the 1770s. Wow, just let it out of the bag. He discovers hydrogen. Troy.
Did you have a date for when Joseph Priestley discovered oxygen?
Oh yeah, 1774. And I believe that, let's see, this hydrogen was discovered just a few years later. Maybe it was,
So now we're at hydrogen.
now we're at hydrogen, yeah. Let me just guess and say 1776. Now, what Cavendish did was he took a pure metal and dissolved it in acid. So he added, he took, say, if you take iron filings, or it works with some other metals too, and then you pour sulfuric acid or nitric acid on them, you will get a gas bubbling up, and you can collect that gas, which Cavendish did, and find that it has different properties than all the other gases that people knew about at the time. It will burn, okay, vigorously, but it's no good for breathing, and and it's very light. Yeah.
What if people tried it themselves to see if it was
well, put it this way: if you had like a whole balloon full of it or something, and you just breathe that, you would feel like you were suffocating because you weren't getting, any oxygen. So that's what I mean by it's no good to breathe. Yeah, the only satisfying thing about breathing is getting the oxygen. Otherwise, you start to feel like you're just holding your breath. Okay, so he, yeah, the other, so let's, let me see, what he does here, say, iron filings plus sulfuric acid well, in addition to, you know, whatever happens to the iron and the acid here, I mean, he's still got a bunch of stuff left, but he gets out a gas when he pours the acid on the iron filings, and that gas is the gas burns, not breathable, and very light. Now, it was at this stage, in the 1770s, that chemists started being more careful when they generated chemicals and chemical reactions to start weighing the various chemicals that they generated, because this also gave some clue to it was another property that they could study, and sure enough, the gases did differ in their weights, and this one was extremely light. It had almost no weight at all compared to the other gases. So that was people thought that was very interesting. So it was clear that this was a brand new kind of gas, and it turned out to be hydrogen. True.
How do they weigh gases?
How did they weigh them? Well, if you put this, like a container, if you have a container full of this gas versus a container of air, you can put it on a scale. See that the container, if you have two containers the exact same size, one of them's full of hydrogen and one of them's full of ordinary air, and you put them on a balance scale, the scale will tip toward the one, the air will sink and the hydrogen will rise. Okay, now Cavendish does another remarkable experiment with this new gas of his. He takes it and combines it with oxygen and sparks the mixture with an electrical spark to see if there's some. He knows that this this will burn and the oxygen will burn, and so he thinks, well, I'll put them together and spark them and see what happens. What do you think happened?
Hot water?
Yeah, he got water.
H2O.
Yeah. Now that's pretty amazing. You talk about blowing a hole in the idea that water is a pure element. Okay, that was the old Greek idea. Here, chemists in the late 18th century now can generate this hydrogen gas, generate another gas oxygen, which is one part of air, put them together, spark them, and get water out of it. Now that's clearly seems to be showing that, you know, water is not a pure element, right? Water is a compound of these two gases that they've discovered. And he even Cavendish went further and measured, you know, how much hydrogen and how much oxygen went into producing this this water, and he found that that 2 liters of hydrogen would combine with 1 liter of oxygen to produce, say, steam. Would produce actually 2 liters of steam. So so he actually quantified this. That's worth writing down. So say 2 volumes hydrogen plus 1 volume oxygen would go to 2 volumes steam, say, or right, so water in gaseous state. So that people didn't know quite what to make of that at the time, but that was interesting. Now I mean, you've all heard that water is H2O, right? So it's 2 parts hydrogen and 1 part oxygen. Cavendish was the first to experimentally show that. Okay, so next time I'll talk about a French chemist by the name of Lavoisier, who was really the father of modern chemistry.